Greetings to you. We will continue our discussion on the electromagnetic radiation and its interaction with the matter. In the last slide, we had seen how we can calculate the energy of the electron. Here we had stopped at this slide, but I want to go back and spend a few seconds on the previous slide. So, what we did was, after looking at most of the electromagnetic radiation properties, we have decided how to characterize the electromagnetic radiation. So, we did two examples, and the second one is this. I did not spend much time on this. So, the idea is to calculate the energy of the 430 nanometer photon of the visible radiation. This 430 nanometer is sort of reddish orange color, okay, orange color. So, if you see color, any color in the sky, for example 430 nanometers in the orange color, you can actually calculate what is the energy of that radiation. So, you use a prism and then pass the radiation, collect the radiation of the orange color, you can calculate what is the energy of that radiation. Similarly, you can calculate for blue color, violet color, etc. So, the information formula is very simple. E is equal to hc by lambda. This is Planck's constant. This is velocity of the light in vacuum, 3 into 10 raised to 10 meters per second I have put. Otherwise 3 into 10 raised to 10 centimeters per second also we can put. Here I have put joules and the Planck's constant in joules seconds, and there you have to divide it by wavelength, that is orange color. So, orange color wavelength corresponds to 430 and nanometer, that we have to convert it into meters again. So, meters by nanometers. So, the energy comes to 4.6255 into 10 raised to minus 9 ergs. So, but that is expressed in kilojoules per mole. So, the energy of each one will correspond to, each photon would correspond to 4.6255 into 10 raised to minus 19 joules per photon, and that is the so many photons per mole. That is, if one molecule of the substance is giving out radiation, how many radiation atoms are there? There will be 6 into Avogadro's number, 6 into 10 raised to 23. So many photons, so many molecules, so many atoms. So, so many photons per molecule, multiply it by, convert it into kilojoules. So, that you will get 278.4551 kilojoules per mole. That is how you can calculate the energy of any wavelength corresponding to electromagnetic radiation. So, I can ask you in the test to calculate the energy of a photon per mole corresponding to different colors. So, be prepared for such small surprises in the tests if you plan to take the test, but even otherwise the information is very useful. So, now after having studied all this, I had put on this slide stating that the quantum theory originally proposed for blank body radiation, etc. This I have already given you enough introduction. So, it was extended to explain the emission and absorption processes. This emission and absorption processes are closely related to our topic of interest, that is ICP, inductive coupled plasma atomic emission and absorption. So, the rules remain the same irrespective of whether it is UV, visible, IR, whatever it is. So, what are the essential postulates? The essential postulates of the quantum theory are ions, atoms, molecules exist only in certain discrete energy levels. and when it changes its state, it absorbs or emits the radiation exactly equal to the amount of energy difference between the two states. Okay. So, if it gets excited, it absorbs the radiation. If it gets comes back to ground state, it emits that radiation, but it will be exact quantity. So, if we know the energy, we can calculate the amount of the radiation that comes out and vice versa. So, during the transition from one energy state to another, the frequency or the wavelength of the radiation is related to the energy difference. This we have already covered, and E1 minus E2 is equal to Hc by lambda. So, for atoms or ions in the elemental state, that is uncombined atoms or atoms from which electrons have been removed, they are known as ions. The energy of any state arises from the movement of electrons around the nucleus. Such energy levels are called electronic energy levels. Molecules exhibit, apart from electronic energy levels, vibrational and rotational energy levels. That is, each electronic energy level is associated with number of vibrational energy. You can imagine a big building with from the ground floor, first floor, second floor, third floor. So, each floor represents some sort of an electronic level, but each floor, to reach each floor you have to climb number of steps. Those steps you can imagine as made up of vibrational energy levels. Okay. Now, suppose you divide each step again into still smaller steps, so that smaller people or ants and other things, small animals can go through stage by stage. They are something like rotational vibrations. So, each vibrational and rotational energy level corresponds to a particular electronic energy level. So, the lowest energy state or a molecule of an atom or a molecule exists at room temperature. That is, all molecules and atoms contain the electrons at the lowest energy level at room temperature. This is called as ground state. Higher energy states are termed as excited states. So, detectors used in ICP-AES work on the principle of photoelectric effect. These include photomultiplier tubes and diode array photodetectors. So, the job of the detector is to convert the photons that fall on the photomultiplier tube or photoelectric effect or photodiode array, is to convert the photon back into an electrical signal, and that signal can be recorded. It will be in voltage or ampere or whatever it is, or resistance, any of the electrical properties. So, the use of photodetectors are part and parcel of all instruments which work on the electromagnetic radiation. We will come to that again when we describe about the instrumentation for ICP-AES in particular, because there is lot of theory to be learnt about it, but I have already covered most of it in my previous course, that is on atomic absorption. Now, what I want to do is I want to shift again your attention to the nature of interaction of radiation and matter. Okay. So, radiation passing through a matter, passing through a on its own in vacuum or in air or in this thing is different, but interaction, how does it really affect the matter? We have already seen that refraction, reflection, refraction and scattering, they are all part and parcel of the interaction only. So, now I want to tell you about the interaction of electromagnetic radiation with a sample, okay, which we want to analyze, because apart from the optics, the radiation also has to react with the sample to generate spectrographic data. So, what we need to do is we take a sample, subject it to a chemical stimuli in the form of heat, electrical energy or light or bombardment, or a chemical reaction we can carry out. So, this stimulus, any temperature, heating or a chemical reaction etc., it causes the analyte species to move from one energy state to another. Now I am talking about the sample. So, in the process, the sample absorbs energy or it emits or scatters. So, information about this can be obtained by measuring the electromagnetic radiation, that is incoming radiation, matter and outcoming radiation. I have three parts. Imagine my head as a sample, incoming radiation is on my left, and outgoing radiation is on my right. So, the radiation comes here, passes through my head and then undergoes some certain amount of transformation, comes out on the other side. So, my sample interacts with the matter and undergoes changes in its energy states. So, that is what we are talking about. So, now look at this figure. This is there are two processes, one is emission, another is absorption. Basically, that is what we have been discussing. I have the sample here, I am putting I am exciting the sample into a suitable state where it can interact with the electromagnetic radiation. So, it may be thermal, electrical or chemical energy. The sample is here. So, the radiation, emitted radiation is collected here, my radiation also comes here, electromagnetic radiation reacts with the sample and the energy comes out, that is photonic energy. So, here what is the difference between the sample, or here the sample, this arrow, green arrow what you are seeing represents a transformation of the sample into a state where electromagnetic radiation interacts with the atoms and molecules and ions. That is why I have written thermal, electrical or chemical energy, and then electromagnetic radiation also passes through that and then emitted radiation comes out. This is the emission. So, what happens here? I have put it in terms of energy levels. This is E1, H mu 1, H mu 2, E1 to E2, and then E2 1 is here. Okay. So, for each transition that takes place here, I have a peak corresponding to absorption, and the dotted lines represent absorption and the lines pointing down are emissions. So, the emission wavelengths I can calculate or measure by using photo detectors. So, this is the whole process of spectroscopic application, how a spectroscope is generated etc., and what is recorded is a response of the wavelength versus its energy. We know how to calculate the energy and how to determine the energy that is coming out. So, I know the incoming energy of the electromagnetic radiation, I know the outcoming energy of the electromagnetic radiation, I can generate a figure like this by plotting lambda versus energy. So, this is absorption process. It is I have the sample here, again I am changing it into a measurable form by supplying heat or temperature or making into small molecules, and then I have the incident radiation coming from the left here, and then it passes through the sample, undergoes transformation, and what comes out is transmitted radiation. So, here the energy is absorbed. Okay. So, even the absorbed energy, the same parameters can be calculated. This here the axis is absorption, y axis, and x axis is wavelength. Okay. So, these are the two basic principles, absorption and emission, that take place here. So, we will talk about emission because this course is all about atomic emission spectroscopy. So, when excited atoms, ions or molecules return to the ground state, the excess energy is released as heat or in the form of photons. If the energy is released as heat, you cannot measure the amount of radiation by photodetectors. Okay. But if it is photons that is coming out, then it can be measured. So, the excitation can be brought about by bombardment with electrons or some other elementary particles. This gives rise to X radiation, okay, X-ray. So, I can use electric current, AC spark, heat source, AC arc, DC arc, furnace, etc. to give rise to UV, visible, infrared radiation. Now, I can also use for excitation a beam of electromagnetic radiation. This produces fluorescence. Why? Because sometimes the wavelength coming out is at higher wavelength and lower energy after excitation. So, that produces fluorescence. So, exothermal chemical reactions also produces what is known as chemiluminescence. Both these systems I have addressed in my MOC course on spectrophotometry. You can look up the details in that course. Now, there are different types of spectra. The response what I was talking to you about the response of the electromagnetic radiation with respect to wavelength. That is what is a spectrograph will do, and what is a spectrometer will produce, and a plot is known as spectrum or spectra, number of slots, those things. The atomic and molecular spectra are usually plotted as the function of the relative power of the emitted radiation. Okay. So, that is with respect to wavelength and frequency. A typical spectra will have three components. One is it can be a simple sharp line, or it can be a band, or it can be a continuum. You cannot make out a specific part of the spectrum. Okay. You cannot make out the specific part of a spectrum. Okay, this is an absorption or this is an emission. You will see a bright light somewhere or a peak with a simple, with no maxima or minima. So, that is known as continuum spectrum. I had shown you in Fraunhofer lines, the lines and bands and continuum spectra earlier. You can look it up again. So, what is a line spectra then? Line spectra are a series of well defined peaks, but they are so sharp that you cannot really think it is a curve with a maximum or a minimum. So, it just goes like this. So, our human eye is not capable of distinguishing the rising part or falling part of a peak, that is known as line spectrum. Now, band spectrum is another one. So, there you can see it contains a number of several groups closely spaced, but not well resolved peaks. I had told you about the small energy difference using spectral using vibrational and rotational energy levels. Those things, if they are visible in the spectrometry, in the spectrum, then it looks like a nice Gaussian curve. You can I have shown you such curves earlier also, but we will see them more and more, and such spectrums are very common in UV visible spectrometry and atomic absorption spectrometry also. So, the continuum part of the spectrum does not show any peaks. Okay. So, but line spectra and band spectra, they are all both superimposed in the spectrum, in the continuum area. So, what is we will spend a little bit about line spectra. Line spectrum of atomic particles are preferably obtained in the gas phase. That means, the particles, atoms must be well separated in the gaseous phase. Any substance has got three states. One is liquid state, another is gaseous state, another is solid state. In the solid state, all the atoms are compacted together. In the liquid state, they are in a state of motion, and in the gaseous state, they are in the, they occupy the volume that we give, where the total volume is occupied by the gas, by the sample. That means, each atom or molecule is free to move around in a given volume. So, the gas phase, because they are so free, the spectrum particulars become clearly visible. So, line spectra are maximum seen in gaseous samples. Okay. So, typical width of these peaks are of the order of 10 raised to minus 5 millimeter. That means, we can see only 1 millimeter difference in our scales, right. If you take your compass at home and look at the scales, 1 centimeter you can see, 1 millimeter you can see. Less than 1 millimeter you can see with difference with a good eye, and if you take a magnifying glass you can still see 1 millimeter nicely, but that is 0.1 of 10,000 times thinner than that, 1 millimeter. You divide 1 millimeter into 10,000 parts, that is 10 raised to minus 5 millimeter, and that you cannot see with our naked eye, each marking. So, we need some space for marking also. No? The markings themselves will be thicker than the peaks. So, 10 raised to minus 5 nanometer would be approximately equal to 10 raised to minus 4 angstroms. So, the line spectra are more maximum obtained by X-ray, and they are produced by the transitions of electrons to innermost orbitals. Therefore, it is a characteristic of the element, but not of the compound. Why? Imagine I have a substance, okay, sodium chloride. Now, sodium chloride is a molecule, crystal. It has got sodium ions and chloride ions. Suppose I have molybdenum, then it has got only molybdenum, but it is a solid because it is a metal, we all know it. Now, when an electron in a molybdenum metal falls down from higher energy level to a lower energy level, it is the characteristic of the molybdenum that we see in terms of a spectrum, because it contains nothing else. Similarly, several molecules, if they are subjected to X-rays, there will be line spectra, but the line spectra correspond to the characteristic of the elements that are contained in them. Okay. So, it is a characteristic of the element, but not of the compound. So, similarly in UV visible region we do get line spectra for gases, but there the transition will be from electronic energy levels, from one electronic energy level to another electronic energy level, that is the transition. And then we have what is known as band spectra. So, where do band spectra come from? Radicals and small molecules like carbon monoxide, carbon dioxide, nitrogen molecules, small molecules, containing 2 or 3 atoms. You can imagine many of them like water. It has got only 3 atoms, H2O, ammonia. So many small molecules exist, and such radicals and small molecules usually exhibit band spectra. These peaks are associated with vibrational energy levels. So, the lifetime of the vibrational energy level is also approximately 10 raised to minus 15 seconds, but this is very short compared to 10 raised to minus 8 seconds for the electronic energy change. Okay. So, the transition always occurs from the lowest vibrational energy level of the excited state to any of the vibrational energy level of the ground state. Okay. Now, imagine I have number of vibrational energy levels. Initially, transition from excited state starts from vibrational energy level to lower and lower vibrational energy level, and then the electronic transition will take place when it falls to the lowest vibrational energy state of the excited electronic state. So, how does it happen? It happens by collision. In the gaseous phase, lot of gases, gas molecules are moving here, there, everywhere in random directions. So, they may hit each other, and during that time the vibrational they lose energy in the form of heat or something, and then they come to the lower vibrational energy levels. So, there they once they reach the ground electronic energy level, then only the emission will take place. In the continuum spectra, you do not see anything, you will just see a bright beam of light. For example, radiation from a black body when heated to incandescence. You can imagine a normal light bulb. Nowadays, everybody uses CFL and LED lights, etc. Just a few years back, people were using tungsten lamps. That is Thomas Alva Edison's discovery, tungsten lamp, carbon black lamp, etc. And there, whenever you pass the current, the resistance goes up, it gets heated up, and you will see only a bright light like what you see in CFL or something. But tungsten lamp would give you somewhat yellowish light. So, but you do not see any other light. So, it is a continuum light radiation containing several wavelengths of the electromagnetic radiation belonging to the visible range. Okay. So, the black body radiation produces a continuous light, bright light, yellow light or something like that, undistinguishable from each other. So, the energy peaks shift to shorter wavelengths with increasing temperature. I keep on increasing to a higher temperature, the energy peak will come like this, and then it shifts to shorter temperature. So, heated solids are important sources of UV visible and IR radiations. So, if I want to produce ultraviolet range, I need to take a substance and heat it to high temperature. Similarly, for IR, similarly for visible range. So, these are the sources of UV, visible and IR ranges. So, I can, when I build a spectrometer, I need a source of electromagnetic radiation. Then what I do, I take a small amount of sample, tungsten lamp, heat it. It gives out continuum background radiation containing several electrons. So, that is my source. So, I need a source while building a spectrometer. So, we do not have to, it is the building a spectrometer or something like that is not rocket science. We just have to understand the different phenomenon of electromagnetic radiation and choose wisely. That is the beauty of a spectrometer. So, now absorption of spectrum, we will discuss about it for a very short time. So, absorption of electromagnetic energy by atoms, ions and molecules promotes them to higher energy. This we have already seen, and then we have already also seen the spectrum, how it generates, but absorption spectra differ widely in appearance from sharp peaks to smooth continuous curves. This also we have covered already. So, it all depends, the nature of the curve depends upon the physical state, complexity of the molecule and the environment of the sample, that is whether it is heated, whether it is molecules or droplets or aerosol, whatever it is. So, that is that depends upon us to convert the sample into a suitable measuring state. So, an atomic spectrum of an element results in only a few simple lines, and as excitation can occur only at electronic levels. So, or the outermost and or bonding and bonding electrons only. So, molecular absorption spectra are more complex. This we have already covered number of times now. See, the idea is the same phenomena, when they occur, they can be used as different aspects of a generating a molecular or atomic spectra. So, that is what we are discussing now. So, gases we can generate UV visible, we can generate infrared, we can generate molecular absorption peaks and so many other peaks. So, molecular absorption peaks involving electronic energy are fairly broad because molecular this thing, owing to the presence of vibrational and rotational energy levels. I keep on repeating these things so that it must remain embedded in your memory. Okay. As a result, the spectrum of the compound consists of number of closely spaced absorption lines that constitute a broad smooth absorption band, giving the impression of a continuous spectrum. So, pure vibrational energy, if I have to measure, I can see it in the infrared spectroscopy. Only vibrational energy, not rotational or electronic. Electronic you will see it in the visible range or UV. But if you wish to see the absorption vibrational energy levels, then that energy level is reflected in the IR spectrum. Okay. So, pure rotational absorption spectra are observed in microwave region, that is not even IR. IR is too much energetic with respect to rotational energy level. So, if you wish to see pure rotational energy level, you should go to microwave region, examine the spectrum in microwave region. So, we are discussing about the absorption spectra obtained in different regions. One is UV visible, in vacuum ultraviolet and X-ray we get only the line spectra, and in UV visible we get band spectra. That means you will see a nice Gaussian curve one after another depending upon the intensity and type of transitions. And third one is the and where the energy differences are still less. So, that is next energy level, and after the electronic is vibrational. So, vibrational energy levels you do not see them in the visible range, you will see them in the infrared, that is the next range of electromagnetic radiation. So, this is the vibrational energy level changes are the basis of infrared spectroscopy, that we will study later in some other course, not now. And then there are pure rotational spectra, still lower energy levels than higher than vibrational. They are obtained in the observed in the microwave region. Okay. So, these things are all fairly simple, but require different spectroscopy, different optics, different sources, different optics, and then different detectors, different recording systems, everything changes in each and every system. So, electronic spectral transitions gives rise to spectrophotometry, UV visible. So, wavelength of the energy source does not change here. What comes in, I may send in an electromagnetic radiation, pass it through the sample, collect the radiation that comes out after the sample is treated. So, the total amount of energy corresponding to the molecular band, which is characteristic of the element, is measured. That means, incoming energy is so much, outgoing energy is so much, difference is what is absorbed. So, that is UV visible spectrophotometry. So, the only change in the intensity of the incident beam and transmitted radiations are measured in UV visible spectrometry. Sometimes the absorbed energy of a molecule is re-emitted as a radiation of lower frequency or longer wavelength. This I had already referred in my last class, and this is results in the fluorescence phenomenon. So, energy changes occurring in electrons and nuclei under a strong magnetic field are best studied by nuclear magnetic resonance spectra or electron spin resonance technique. So, these two are again specialized techniques, not really useful for routine analysis, but for research purposes they are very useful. Which one? That is NMR, nuclear magnetic resonance, or electron spin resonance. Both of them address different aspects naturally. So, UV visible spectrophotometry, the time frame of absorption is 10⁻⁻15. Energy exchange occurs by the interaction of potential energy components of the molecules via the movement of electrons, which can be represented as single vertical line in the energy diagram. This and all we have covered here briefly and in more detail in the earlier courses. So, the absorption bands occur only at definite values corresponding to energy differences, quantum mechanics. Okay. So, absorption terminates when the solute molecule loses its energy to the ground state molecules of the solvent molecules. Once the molecules get excited using electronic levels, sometime or the other whatever goes up should come down. Okay. So, when they come down to the ground state, the excess energy must be lost. The excess energy is lost to the solvent molecules or to the same molecules, okay, but it is not lost in different quantities, exact quantities, but it is not as electromagnetic radiation. Electromagnetic radiation can get converted into, it is a form of energy, it can get converted into kinetic energy, potential energy, and then the heat energy, so many other ways it can get lost, collisional energy like that. So, by radiation, these are known as radiationless processes. So, the excess energy is transferred to the other molecules through collisions and or vibrational and rotational modes within the excited molecule. It can be through other molecules or its own molecules. So, both these relaxation processes are accomplished by loss of thermal energy, that is the mechanism. So, there is a molecular orbital theory which explains these things. I will try to attempt it with respect to this course in a very short manner. That is, when two atoms react to form a compound, electrons of both atoms participate in the bond formation. This we have discussed earlier, and occupy a new molecular orbital where bonding electrons are associated with molecule as a whole. Okay. So, this is called as bonding orbital, and in bonding orbitals the energy of the molecule is at its lowest level. So, when I excite the electrons, excite the molecule, the energy of the electron goes from lowest to next higher energy levels. So, during bonding most of the molecules are stable at room temperature, that is the bottom line. For example, water at room temperature is very stable, it will not go away, right. So, similarly carbon monoxide, sulfur dioxide, nitrogen oxides, ammonia, all these elements, carbon dioxide, all these elements are very stable at room temperature because they are all bound by bonding orbitals, sigma bonds, pi bonds, etc. So, simultaneously whenever a bonding orbital is formed, there will be some sort of a anti-bonding corresponding anti-orbital automatically generated. It is just like having a note, one 10 rupee note, or though you pick up one side, other side also you automatically pick up. So, it is like the moment you have a bonding orbital, there will be another bonding orbital. It may be occupied or need not be occupied, depends upon the state of the atom. So, but it is there all the time. So, anti-bonding orbital is also formed, which are usually vacant in the unexcited state or in the ground state. So, a covalent bond may be formed by the combination of s orbital or p orbitals, because most of the electrons are contained in the most of the electrons are contained in the are formed using s orbital or p orbitals. A s and s orbital of two hydrogen atoms combines to give you a molecular orbital, sigma bond. S and p orbital will give you a pi bond. P and p orbital will give you a pi bond. So, s and p orbital will give you a bond which is ground state, but oriented in space between s orbital and p orbital, something like this in dumbbell shape. S orbital is round, p orbital is a dumbbell shape, x, y, z direction. So, a combination of electrons from s orbital and p orbital will give you a bond in between the space of it is neither in s nor in p, but it is a vector combination. So, the corresponding anti-bonding orbitals also will be there at higher temperature. They are designated as sigma star or pi star. So, valence electrons not participating in chemical bonding are there in almost several compounds we daily come across. For example, oxygen in water is having only 2 bonds, H2O, HOH. Now oxygen has got another 4 electrons extra. They are known as non-bonding electrons. They are not bond with any other element. So such non-bonding electrons are there present in nitrogen, chlorine, sulfur, phosphorus and many other elements. They are known as N electrons, non-bonding. So in organic molecules, non-bonding electrons are located in the atomic orbitals of these elements: nitrogen, oxygen, sulfur, halogen, etc. So here is a typical presentation of bonding and non-bonding orbitals. For example, here I have an atom A, here I have an atom B, and when both of these are combined to give you pi orbitals, so what I get is something like this. The bonding orbitals are like this and anti-bonding orbitals are like this. Some lower ones represent the ground state, higher ones represent the excited state. So this is sigma, this is sigma star, pi and pi star. Similarly, this is again another type. This you can see, this is the plane of the atom. There is a dumbbell shape, one above the plane, one below the plane, another pi orbital of another compound in the same this thing. When they are bound together, when they form a compound, they come very close to each other. That closeness is controlled by the electronic properties of the atoms. That is, if they come too close, electrons will start repelling. If they come still closer, nucleus will start repelling. So it has to be some sort of equilibrium distance, and as the electrons, as the atoms come nearer to form a bond, the energy comes down. So the compound energy of the compound molecule is always like this. So the combination of these two lobes of the top will give you a shape something like this. Okay. And this is another shape which is below the axis. The axis is represented by XX, green color. So far we have discussed introduction, atomic structure and electromagnetic radiation. The electromagnetic radiation has two parts. One is the definition and parts of electromagnetic radiation and their interaction with natural materials, with matter, that is air, glass, prism, diffraction with the gratings and all that. And then we have also discussed about the interaction of the electromagnetic radiation with the sample which we want to take the spectrum. So far whatever we have discussed will form the basis of the instrumentation of the ICP, inductive coupled plasma. So we are going to do sort of Ranga Pravesham for the actual hardcore part of the matter now. So now I want to correlate everything to the ICP, that is our next module.